Where's the share button? Okay, we're live.
Um,
Okay. Let me get into here. Okay. Okay, we already got 33 people. Um, can you guys hear us? You should be able to. And you try saying something, Oem.
so hello, and hope you guys have a good time today.
Okay. Awesome. It looks like people can hear us. Um, looks like Oem. All right. So cool. Um, I'm gonna start off with some questions. So, what? I guess. How are the ways time could end?
Huh. So yeah, that's a very short question, but I think if someone was to answer that in its full entirety, that would take quite a week, to be honest. Uh, but uh, but like thinking about it, I mean. Firstly, we would have to think, how do we define time? Like, do we define time as a construct which originated with the universe? Or like, was there a construct of time before this universe began? Or like, will it remain after this universe will, possibly die in some way? Because our definition of when time will end or like when time will start will completely depend on how we want to define what time really is. So if we define time, let's say from the start of the Big Bang, so we say that time started when the Big Bang happened 14 billion years back, let's say, right? So by some estimates we can say that there is uh, some some finite value of time, let's say billions and billions of years in the future, when the universe might end in one of the ways in which people have investigated. Cosmologists have put forward various ways in which the universe can end. There is the big rip, there is the big freeze, there is big crunch, and all of that. So if we tie the definition of time with whatever started off with the Big Bang, then of course it will end when the universe itself also ends. But that is short-sighted in the sense that we are defining time completely based on this universe, because I mean then you have the idea of multiverse. And if you are concerned with the multiverse, then let's say this universe ends. So I mean, then is time just tied to the idea of one universe, or like is it a multiversal construct? Because if it is a multiversal construct, then it doesn't matter whether a universe lives or dies. Time itself stays on until the multiverse somehow dies away. So I think saying how time will end is quite a far-ranging question, of course. and depends on how one wants to, define their own paradigm of what time really is. I mean, then you have, some physicists. I mean, some of the greatest minds of, like, it's 18th century, 19th century. Those guys just thought of time as, some variable in their equations. I mean, they didn't pay much heed to its physical meaning, and it wasn't until Einstein came along that, with his theories of relativity, that, we had time dilation and stuff like that, that people started to realize that, oh, it's not only the clocks which are, like made by some, industrial people, that, they like time is not just, something they have created to, like, sell more clocks, but, it is probably something which has a deep physical meaning, tied to the very nature of our space-time fabric. And right so I think my final answer on this would be, like, twofold. One, I would say that if we have a definition of time which is tied with our own existence, then, that ends when this universe ends. But if our definition of time, precedes, or, goes beyond whatever our universe is, then, essentially it doesn't ever end, because our existence doesn't hinder the existence of time as a whole. So yeah, that would be, one answer. I mean, it is indeed a very simplified version of this, of course, but I mean, that is pretty much essentially how things would be in a general sense.
So it sounds like basically like you cannot ask the question when will X end if you don't even know what X is.
Yeah.
Um, I had a bit of a theory. I actually got into an argument with one of the editors of Nature magazine about this. He was big into multiverse theory. Um, and I kind of wanted, in terms of attempting to define what time is, I kind of wanted to propose this to you, and I guess maybe get your thoughts on it. My I came up with this interesting idea one day that time is actually the dynamics of quantum entanglement and decoherence, which is like you could say that's information in a way, and then thus information is, you could say, would also be time. And what I would theorize is that, like, is if there is no like quantum decoherence I don't know if I use the word exchange, but if none of those dynamics are going on, then there's one could say there's no time. But that is just one theory. Um, have you? I know you've.
All right.
Yeah, go ahead.
Right. So I think, I mean, firstly, I would say that, I would just explain what decoherence and, like, entanglement is,
Okay.
just to be clear to,
Okay.
everyone. So I mean, think about this. So, like, let's start off with the idea of decoherence. So, we have this, this very interesting thing when one starts to study quantum mechanics. That, let's say, we both are in a room, right? And let's say we close our eyes. Now, if we close our eyes, we would have this premonition that, when we open our eyes, anything could be possible, right? It could happen that, our room opens and, let's say, John Cena walks in. I mean, of course, if he walks in, we wouldn't see him, right? But let's say if we have someone like, Michael Jordan, I mean, someone like, let's say Tom Brady coming in, right? So if those guys walk in, right? So I mean, we would be happy, but we know that, if we, close our eyes and, leave the room of the door open, the door of the room open, there wouldn't be much of a chance that any of that would happen. But until we don't open the eye, right? We can't be sure that some particular thing would not open, right? Or, like, some particular thing would not happen. So in a similar way, quantum mechanics is like
It's like a
is quite weird in that sense, because it says that until you do not complete any kind of experiment, you cannot be sure about what the experiment would really give you, right? And so let's say if we were in the quantum world, there is a good chance that if we close our eyes and then when we open it, we could meet Ronaldo, we could meet Messi, and people like them. uh, while when we talk about that in the quantum realm, it could happen that, let's say, you are doing some experiment on an electron, right? So you have a set of possibilities that the electron could take this particular configuration, let's say, right, after the experiment. But the cool part is, and this is quite interesting, that our mere idea, our mere act of measuring the electron, our act of actually doing the experiment changes the result of the experiment.
hmm
And that seems very absurd, right? Because I mean, nature should not care whether I'm looking at it or not. It should be as it is. But somehow at the quantum level, it does. And so what happens is, out of the infinite possibilities, the electron eventually decays to one possibility, which I have seen about it after my experiment has been done. And so this decay of the wave function, I mean, I'm talking in the technical sense, is known as quantum decoherence, essentially. Then the idea of quantum entanglement. So it was very beautifully put by Pauli once, who was also a great physicist, that basically, if I were to flip my hands like this, right, I have just impacted some, let's say, some particles who are let's say millions of light years away from me, just about right now, just by moving my hand. And people ask him, why are you saying so? And he said that if particles over here are entangled with particles millions of light years away, then they just have to respond to any kind of stuff happening on them. So it's kind of like this. So let's say, for example, I mean, so I'm not sure, I think, most of us would have, seen the prime of WWE, right? So, the ruthless aggression era, right? When we had people like, Kane, Undertaker, and all of those people at their prime, right? So I'm pretty sure you would have also seen that, right? Yeah. So like there was this storyline where they had like, I think they had like two Kanes or like two Undertakers, and if you do something to like one of them, the other one gets hurt or like something like that.
Like in like WWE.
Yeah, yeah, yeah. So
Okay.
I'm trying. Yeah, yeah.
I thought you were talking about
Uh,
Cain and Abel or something for a second.
no, no, no. I'm just trying to make like a case for like how entanglement could be motivated over in this case. And like, of course, it seems very far-fetched that we're talking about how WWE can help us understand entanglement, but like, just bear with me for a second.
Okay.
So there was this storyline that one wrestler has this copy, right? And that copy and the original wrestler are like in a feud with each other, because that's how WWE works. And now eventually, if you do something to like one of those people, the other one responds. I mean, they have to respond in some way or the other.
Yep.
So like in that way, entanglement is like similar in that sense, as far-fetched as it sounds, but like it's like more deeper in the sense that let's say I have an electron right about here, right? And now if that electron is entangled with some other electron anywhere in the universe, if I were to somehow, disturb this electron, then the electron which is entangled with it, far, far, far away from, from me, would have to immediately also respond. So, me disturbing this electron will indirectly disturb the electron which is far away from me, which which is, far away from, my own influence area, let's say.
When you say the
Uh,
word disturb, do you mean measure?
Yeah, I mean, yeah, in a crude sense, I would say that, yes, I mean, in a technical sense, it would be measure, but like I just wanted to, use like a simplified language for that.
Okay.
Uh, yeah, I mean, of course, when we are talking about, doing any kind of, experiment, let's say, in the like on the quantum level, we are really, trying to measure some property of the particle. And so, of course, whenever I say that, we are trying to, see something, see the electron, or like, disturb it, we are really just trying to, find out some particular property, like trying to make a measurement of some particular property
Like the spin,
of the
like
party.
spin or something.
Yeah, yeah, of course, like spin, like energy, and like, stuff like that. But yeah, it's cool that, you make the measurement on some particle over here, and somehow, that measurement, makes the other particle, which is very far away, you know, like, change its quantum state as well. So like that's entanglement. Now let's, get back to your question about your, I mean, on quantum entanglement, and like, how, you know, that alongside decoherence could, be on the, on the, like,
Or I
on the
guess
sides of time.
it's like
So
like the
yeah,
entanglement and the disentanglement. And also, I think I wanted to point out, and I believe this is true, that like if something's entangled, it's not necessarily like it's not like a binary thing. Like it's entangled or not. It's like there's some degree of entanglement,
yeah,
or and disentanglement, and that I guess a particle would constantly be doing that with its environment. Or I guess when we do these experiments, we have to isolate, for example, the electron and or the particle, such that we can observe the phenomenon. So
yeah.
yeah,
Yeah, I mean, like making, experiments on entanglement is like a different beast. I mean, we can talk about its like theoretical side in a very, easy way, like we just did. But like, people got a Nobel Prize for, performing an experiment on entanglement. So like, performing the experiment, like, trying to like test it out experimentally is like a different kind of, ball game. I mean, so, you need very sophisticated procedures, as you just mentioned. You need to, isolate the particle, and, make very idealized surroundings to like, have any chance of like, detecting, if there is any kind of entanglement involved, and then, do your stuff. So, like, I'm not even sure, like, if I can even go into the specifics of how, the entanglement experiments are done, but like that's like a different kind of complexity.
yeah,
But yeah, as you mentioned, I mean, even entanglement, it's not like, it's not always like, like two particle thing. So it's not always that, you have an electron, and some other electron, of course you can have other particles besides the electron which are entangled as well. But you can also have, group entanglement. So let's say you have, like, you can have, let's say, you know some particular amount of particles, let's say they are in a, uh, like they're grouped together, right? So you can, think about, like how individually these are, all of these particles are entangled with some other particles, on their own individually, right? And so when you change, the state of this group, when you try to make a measurement on this, like collective set of particles, you also, at the same time make some kind of a, disturbance, or like any kind of, we put it,
Like
to
a
that.
contamination. Yeah.
Yeah, I mean, yeah, indeed. I mean, yeah, you can say that. You like when you disturb, contaminate, measure this particular set of particles, you are doing the same thing indirectly with the other set of particles which are far away from you. So yeah, that's quite a deep thing. Uh, so like, how do you think about this, on the interface of time?
Because I guess it's the only thing that, and this is pretty simplified, but like it doesn't quantum entanglement doesn't move like at a meters per second. Like the reactions don't happen at meters per second. If you were to like maybe put placeholders in there, it would happen at 0/0. Um, if that even makes sense. And then
Okay.
I was like, okay, well maybe the if you just like let's say you assume that quantum entanglement or in the disentanglement is information. So is information in its essence. Um, if you think of like a fly has all these eyes, and they're made for picking up spatial information, and they can render more spatial information in the same time frame than we can kind of experience. And one of my theories was that, for example, because of that, that's an evolutionary adaptation, which means that they can. It's very hard to kill them because they experience the information in a spatial way at a much greater resolution than we do, due to all the information they're gathering. Um, and then I'm like, okay, is it like? I guess it comes down to defining what time is, but it was kind of a that was just it was a theory of mine. um,
No, I mean that's very interesting, to be honest. And particularly, this fly bit of yours. I mean, like you mentioned about how flies, and like like in a sense, quantum entanglement could have some kind of a quantum biology aspect here as well. Is
mhm.
quite interesting because uh, I will share that paper with you, and you can probably make a whole different video with that. There was this recent paper which actually discussed how it could be possible that our consciousness, our brains are quantum entangled as well. So let's say let's I mean to give you like good example, I mean, we usually say, right, that we would like to manifest things in our life, right?
Mhm.
So let's say I want to convince someone to like go out with me, right? And so I'm like just thinking about it, and somehow it turns out that like that person says that I mean, let's hang out and stuff like that.
You're
So
you're luckier than me.
I mean,
I
yeah.
get like robbed by girls here.
I mean, I mean, I wouldn't comment on that a lot because I have I have people in Latin America as well, and I wish to visit someday and come back in two pieces. So
Yeah, no, it's you just can't do stupid things. Um,
yeah,
um, okay. So we're gonna have to refresh Zoom in like 5 minutes, but
yeah.
okay. You, what would you say would be? I know you've done a lot of research on the end of time. Which, and you have, and you were telling me about the long freeze. Now, which would you say that might be? And maybe there's some bias there. But that might be like one of your more favorite theories of it, or um, or oh, I lost audio from you actually. Oh no, you weren't talking.
Yeah,
Oh, okay.
I wasn't talking, just
um,
listening.
or like, for example, like I do really like obviously Robert Penrose's CCC just because it's kind of cool. For the audience um, that's basically like at the end of quote unquote time, some magical thing seems to happen, and there's like nothing, and then everything springs together again, as far as I kind of understand it. Um, would you like to talk about like the long freeze, which is your upcoming paper, a bit?
Yeah, sure. I mean, of course, as you mentioned, there is, some kind of a bias, but I would say that, that all of these, great approaches towards the end of the universe, have some kind of a uniqueness to them. I mean, like, like we have this thing known as the Big Rip, where what happens is that the expansion of the universe becomes so rapid that even the individual molecules themselves start to basically fall apart and rip away from each other, and like like the end is so catastrophic that like basically everything, let's say, just gets blown apart, like torn away. Right. So like that is one possible scenario, which is at least mathematically possible, given our cosmological theories. Then there is the big freeze, right? The big freeze is, so it has some aspects of the big rip in it, but it is not as severe as the big rip.
And
Particularly,
what's the
yeah,
difference between the cold death, the idea of a cold
yeah,
death? Yeah, because
yeah. So,
they sound similar.
yeah, so yeah, so in the case of the cold death, we have a proper way in which the universe is like basically eventually everything is eaten away by black holes, and we don't have anything left, and then the black holes themselves also radiate away, and so the universe becomes very cold, right? But in the case of the big freeze, we don't need black holes per se to like kill the universe. And the idea of how the death actually occurs is not constrained to just the idea of black holes, but it is rather constrained on the properties of dark energy. So like for some different model of dark energy, one could have uh, one can prefer the big rip to the big freeze. For some model, it could be the big freeze to the big rip. Then we have the idea of the big crunch and all that as well. The cool part is that in all of these cases, and like the cold death uh, is more of a philosophical idea in that aspect, because it has this very interesting premonition that you need. I mean, the expansion is so rapid that eventually all of the galaxies are like so far away from each other that eventually the big boys of that galaxy, right, all the black holes in that galaxy start to eat their own galaxy, and then when they have nothing to eat, those guys
They just
themselves, yeah, starve to death.
yeah,
uh,
they just
and
evaporate
and
away.
yeah, and so eventually essentially the universe dies. However, in these cases, like big freeze, and the one, the long freeze, which I have worked on with my collaborator Robert Scherer, you know, in these cases, we are not, concerned with just, some black hole being there, or like, eating away galaxies. Rather, the death of the universe is mostly determined by what model of dark energy, one wants to consider. And the cool part is, or the unfortunate part is, that that all of these models of dark energy are at least observationally viable. And so, distinguishing between them is like kind of impossible at this point.
Okay, they all really, unless unless our universe is merging with little bubbles of universes.
That that's a different kind of scenario on its own.
Yeah. Okay. Okay. So I guess your long freeze theory, the thing about it was that um, it didn't really. Oh, one second. Uh, okay, I gotta restart this Zoom meeting because Zoom is a dick. Uh, Give me one sec, guys. We'll open it up for Q&A like super soon too. Oh man, you guys still see him? Oh my god. Yeah, we're about to Zoom screwed us a bit. I'm just waiting on the link for the uh, for the Zoom meeting. What are some questions that you guys have? If you guys want to list them off right now, while I'm okay, I got the link. We're opening this again. Um, oh dear. Okay, and you're over here, and I should try saying something.
Hello?
Okay, we're good. Um, yeah, if I start my virtual camera in Zoom, then it'll go infinite.
Oh,
But yeah. All right. So do you want to try and switch to like a Q and A mode?
sure.
Okay. Let's kind of see what some of these people. Let's see if these guys have any questions.
Also, like just a second.
Oh, go ahead.
My frame rate is fine, right?
Yeah, yeah, it's good. It's about
All right.
21 frames per second.
Oh shit. It got reduced somehow, but I mean I don't know how. I think I should just leave it out.
Okay. Maybe every decision you make out of free will, an alternate version of you that made the alternate choice was split into a different time.
Yeah, I kind of.
Is that are you a alternate timeline kind of guy, or you kind of stick to what you study?
So I think you're like referring to the minimal interpretation of quantum mechanics.
Yeah.
Yeah. I mean, actually, my first ever research, proper research, was on that only. So I really like that interpretation, and that's why I like wrote a whole chapter about that in my book. So I love it.
Interesting. Okay. Um, how could you go into that a little bit more? Like, how does that? Because I never
Sure,
really understood how that
sure,
how that
sure,
worked.
sure, sure, sure. So like, would you like want me to like start off on like on this now?
Yeah, like so, like okay, so you make a decision, and then like an infinite amount of possibilities just kind of
All right,
causes.
all right,
And and
sure.
and also, if you have anything to, I think people have heard this idea before. If you have anything to say that like people likely may not have heard as well.
Yeah, sure,
Yeah.
sure.
Okay. Yeah. I'll let you go.
All right. So like, should I start?
Yeah. Yeah.
All right. I mean, yeah. Let's start off like with a cool quote. All right. So I think all of us would have heard about Richard Feynman, right?
Yeah.
He was like one of the most iconic physicists of 20th century, and at least besides Einstein, I would say he was the most uh, like the one who was always portrayed in the most playful mood, and that is for like good reason. But Feynman said a very good thing that most of quantum mechanics or like quantum field theory, these days, I mean, in the days of Feynman and even today, is just about the idea that you need to shut up and calculate. And what does that mean? That means that forget about what the equations are saying. Just calculate whatever you want to do it, and just be done with it. Now, that might sound like a pessimistic view, but he is spot on because the problem with quantum theories is the following. We get good results, right? We have the Large Hadron Collider at CERN. We have Fermi Lab. We have all of these great particle accelerators. However, and we have good math, right, on them, but we still do not know what the math really means. And so people start to interpret quantum mechanics in their different ways. And there have been various interpretations of quantum mechanics. Note that when I say interpretations, I'm still talking about the same math. Let's say there is an equation. Let's say x is plus 3 is equal to 0. All right. Now, somebody interpreted, of course, that if x plus 3 is equal to 0, then x is equal to minus 3. But then somebody could say that no, x is not equal to minus 3. It is equal to let's say it is equal to 0 plus minus 3, right? So it's the same thing, but like, people, try to like make sense of it in different ways. Now, of course, this X plus 3 example is very simplified, but the equations of quantum mechanics are a lot more complex. And so making sense of what they physically mean has been something which has eluded physicists for 100 years. I mean, we are coming to a point at which quantum mechanics is 100 years old. And so at least we should know what the equations really mean. But yeah, so like that has been a problem. Uh,
Like the original equation where it's a trade off between like momentum and position.
I mean, no, that is just about
Or
the uncertainty principle. I mean,
oh,
that
okay.
is, yeah. But like, equations in general, I mean, you have, the uncertainty principle, you have the Schrodinger equation, and then you have other, proper frameworks of quantum mechanics. So you have something known as the Heisenberg picture, you have the Dirac equation, you have the Dirac picture, and like, if I were to go to the technicalities, it would just be a drag at this point. But but the point is that we have a very good mathematical structure. We have a great mathematical structure, of course. But what that math really means. I mean, it sounds contradictory. I mean, we have been working on this theory for 100 years. So we should know better, right? But somehow we don't. And so like as you just discussed, there has been different interpretations of quantum mechanics, and one of them is the manual's interpretation. So now, fun fact again, right? So manual's interpretation is like one of the most famous theories that has come in physics in 20th century. Now, interestingly enough, the person who gave this theory, he gave it in his PhD thesis. And that is quite remarkable because, a PhD thesis is normally a researcher's, worst kind of, research experience, because, the first time is never so nice, right?
Yeah.
And, and so that is true in research as well. So I mean, normally people don't do, their best work in a PhD thesis, but he did an amazing work, and we are of course talking about it even now. But the guy didn't name this as the manual's interpretation. It was given by his very famous PhD advisor, John Wheeler. John Wheeler was a friend of Feynman's as well, and they had some very good chemistry. However, so the mini world interpretation is the following. So I mean, we just had this example, right? Where if I were to close my eyes, right, and I have my room, right. So then when I have my eyes closed, there is a possibility that when I open my eyes, there would be like Ronaldo, Messi, Dwayne Johnson, anyone coming through the door of my room. But I know that the possibility of that happening is like negligible. I mean, it's not gonna happen.
It's very low probability of that happening.
Right,
Yes.
right, right. But until I don't open my eyes, until I don't measure things,
You
right,
don't.
I cannot be sure, right? So I have to say that there is a possibility. uh Now the manual's interpretation says that okay, you didn't measure, you didn't see Messi or Ronaldo coming through your door, that's fine, but there is some copy of you in some other universe who has just met Messi and Ronaldo, or one of them, or like somebody. And so whatever interesting theory, whatever interesting idea I have, let's say, I mean, Messi and Ronaldo are like good, but like, let's say, if I were to think of Sydney Sweeney or like Ana de Armas coming in, that would also be true. That would also be true.
So,
uh
well, I mean, like,
yeah.
must a many worlds interpretation? I guess it's called a many worlds interpretation. Why, why would that exist? Just
Yeah,
because of the possibility?
that's a great question. And that hinges on the realism of the idea of a multiverse. So if a multiverse exists, right, then we can say that possibly, I mean, if we have infinite universes, then there could possibly be, copies of me and you. I mean, we both could be talking about, some other topic. Let's say possibly we might be talking about baseball in some universe at this point of time, right? So if there was a multiverse, if there is a multiverse, then the manual's interpretation makes sense. I mean, why not? I mean, of course, if
It,
there are
if
multiple UMEs,
if there is if there are infinite, I guess if there are infinite
yeah,
multiverses, then
yeah. I mean,
well, I
yeah,
mean, I guess if anything's infinite, then
yeah, indeed, indeed.
so would it
So
be like we're choosing our path through?
yeah, that's now you're getting to like the really, just questions. You know, this places, questions on the idea of a free will itself. Because if you think about it, if if let's say, I mean, let's say if I were to do something, let's say, right, if I were to do some measurement and I were to, get some result, right? And then there are other, infinite universes where I were to get different results. So did I change my results, or was I predestined to arrive at this result and my copies were like predestined to arrive at their own results? That is one thing which we cannot, answer clearly using using the math, because the math does not say anything on that. That's quite a revelation, right? I mean, you think about, that you're directing your life, and then, quantum mechanics comes in and says that, oh, it could be true, but it could also be true that, that, whatever is happening with you is just happening to this you, while the other users are doing something
So
else.
are you kind of saying because we cannot prove that multiple universes are the multiverse interpretation is not true, that is simply a possibility that it could be true, or is
I
there more
mean,
to it?
the manual's interpretation came out in the 1950s, right? After that, we had, loads of development in cosmology. So, interestingly, the manual's interpretation was not, of course, a theory of cosmology. It was a theory of quantum mechanics.
Okay.
And like in 1950s, these two fields were like very distant from each other. I mean, you wouldn't need the theory of the electron to study the theory of the stars. I mean, people at that time thought so. Then, in the last 30, 40 years, we've had great, tremendous success in cosmology. And then there is this idea of eternal inflation. So, eternal inflation, so what is inflation firstly? So inflation, if I were to put it in the words of the creator of this theory, is basically the bang of the Big Bang. So inflation provides you with that exponential expansion in the very early universe just after the Big Bang, which basically, as the name says, inflates your universe, and makes it big enough for everything to exist. I mean, for stars to form, for particles to form, and all that. So inflation is like very important. Uh, but you know,
Is there a reason that like inflation? Is it just the fact? Is did inflation just? Do we just say that inflation occurred because it had to have occurred to fit our models?
right. Again, a good question. We can motivate the idea of inflation using various ideas from particle physics. So there's this idea of a false vacuum, right? So we can make a case for inflation occurring using that. Then there is the idea that when we had the standard model of Big Bang cosmology, then there was some very awkward questions with it. I mean, like the very first models of Big Bang cosmology, in those models, the universe had to form in a very specific condition, in some very specific conditions, in order for it to exist. And physicists don't like it when normally when you need to make your model act in a certain way to make the universe act in a certain way. I mean, they want their model to like reproduce the universe in a wide range of in a wide range of areas. And when that doesn't happen, they try to look for other models. And so, there was this fine tuning problem. Like, if I were to use the word fine tuning, so fine tuning, really means that that I'm just trying to, tune my model in a certain way so that, I get particular form of reality with it. So the Big Bang cosmology had some problems fine tuning it. uh, then inflation came in, and inflation showed that, if you have exponential expansion in the early universe, then these problems of the universe being created, in a very special way, go away. And you can have the universe just bang, and it will always create the kind of world that we are living in today. So in that sense, you can make a good case for inflationary cosmology. uh, of course, it is observationally very well tested. There have been various observations with various space probes, which have given data to in the support of inflation. But there are various competing theories of inflation. But as of now, when we talk of early universe theories, inflation is right on the top. And it and the fact that it is on the top is very interesting from the point of view of a multiverse. Because as I just discussed with you, inflation means very rapid expansion, right? Very, very, very rapid expansion, but for a very small period of time. Very, very, I mean, like even less than a second, right? So the universe grows very exponentially large in a very fraction of a second, and that is inflation. So, we say that, it occurred after the Big Bang, but what if inflation is still occurring in some part of space-time, right? So this question was pondered upon by the pioneers of this theory, and they came to the conclusion that, once inflation starts in some models, it may never end. And if it doesn't end, inflation is occurring in some part of the in some part of space time every second, even now. And so if that is true, then there are various big bangs occurring in various parts of space time. And so we have essentially an infinite multiverse over here. So yeah. Me included. Right.
Oh, okay, I was muted. Um, okay, let me re-say what I said. Sorry, guys.
Yeah.
Sorry, guys. Okay, so if expansion is something that happens, expansion is something you said. Expansion is something that has to. There are theories that where it's continually happening, and for uh, for that, um, there would a prerequisite for that would be like more big bangs. By the way, guys, the expansion is like what happened, I guess, a few seconds or something after the Big Bang occurred. It just I I pull up a graph, but I don't want to mess up my OBS right now. It just the universe just went. Um,
Not a few seconds later, not a few seconds, inside a second of the Big Bang, inside a second of the Big Bang.
okay, okay, okay.
Right.
Like just Okay.
Yeah.
Um, so, okay, that happens. And then what so how do these guys arrive at a theory that expansions are continually happening besides mathematical gymnastics?
Right, right, right. Of course. Yeah. So, you just took away a big part of my answer, right? That would be that would be math, right? But yeah, I mean, even besides math, you can actually motivate it in a certain sense.
Okay.
So, so, so,
Like
like thinking of it from a physical point of view,
okay.
inflation occurs when, there are some instabilities, in some part of space-time, right? And I'm using a bit of a simplified language over here, right? But those instabilities, those kind of states are, yeah. What?
Instabilities.
Yeah. It is a bit of a simplified language because if I were to use the actual language, it would just be haywire. So like think of this. I mean, let's say we have a very huge trampoline, all right?
Hmm?
So if there was, let's say, if I were to just put a very heavy ball, right, or like a very heavy collection of balls in one part of the trampoline, right? And just make all of them bounce, right, on that particular patch of the ball together, then then that particular patch would be vibrating for a few seconds after those balls have just bounced on them. So in a similar sense, when the Big Bang occurs, so we usually think of the Big Bang as let's say like boom,
Yeah.
right? But inflation says that that is not quite true. Inflation says that the Big Bang was like this, and then inside a very small time which we call the Planck time, right? So inside the Planck time, which is like 10 to the power minus 43 seconds after the universe was born and all that,
Yeah.
right? The universe was like this. It was very small, and then all of a sudden we have inflation,
Okay.
and it expands the universe to like hundreds of orders of magnitude, and that is huge, right? Now you can say that of I mean, what's the, what is the physical basis behind that? I mean, you just motivate things from your math, and you get your grants, and you get your your PhD thesis and all that, and you just go away. uh, but there is a good physical backing behind that, and like all of that is like related to the particle physics side of things in the early universe. So uh, you know one way to actually understand the evolution of like part of like the universe from the particle physics side is to take quantum field theory, right? So when we start to consider quantum fields in the early universe, we can show that there could be some quantum field in the early universe which can drive such an expansion, right? And we can also show that such a quantum field will then eventually decay very quickly, and so its signature would not be much relevant in the current universe. So we would be thinking what happened, I mean, at the time of inflation. But if such a field was there, we would see its imprint on something known as the cosmic microwave background radiation, which is like the last light from the Big Bang.
Yeah. Yeah.
And indeed, and
There are some
indeed,
there's some weird
yeah,
stuff in there.
yeah, and indeed, we have seen uh, the signature of such a quantum field in the map of the cosmic microwave background radiation, and that is like the biggest and the strongest point inflation has over its competing theories, because it can show its imprint on physically relevant data, And that is quite a strong thing when we are doing actual science, because we want, our theories to be consistent with whatever data we have, with whatever observations we do, and inflation stays on that. So it has a very exotic physical motivation, but somehow, it also makes sense experimentally.
Okay, okay. Let me there's a few questions in here
Yeah.
that I want to let me try and get these. I've heard of this one before. I don't mean to interrupt you. It's just
Oh,
trying to
no,
get these.
no, no, no.
Okay.
That's fine. That's
So
fine.
this guy says one portion of the universe is expanding towards other areas which are contracting. I'm not contracting. Galaxies in our visible portion are accelerating towards non-visible portions, presently crunching. I think maybe I could rephrase the question as: does it appear as if certain parts of the universe, from our perspective, are expanding more quickly or more slowly than others in different directions?
All right. That's a good question. And that would make for quite like quite some interesting mathematical gymnastics, right? Right. Uh, but
I'm
yeah.
sorry to
So
use that word.
no, no, no.
Yeah, yeah.
It's actually good. It's actually good, and we use it. Even like professional theoretical physicists like use it, because sometimes we are like literally just playing around with the math. So, so it's actually a good thing. So yeah, yeah. So if I get this clearly, the person is trying to say that our like galaxies are like expanding away, right, to
Uh,
the non-visible regions, and the non-visible regions are like contracting,
well, I think it would be simpler to just say like, um, I mean, do you see the chat or
right? I can see it. I'll have to probably use my phone for that, but I can see that.
you said you'll use math for that?
No, no, no.
Oh,
No, no, I said I will probably have to use my phone for that, but I can see that right away.
okay, I can send you a link to this.
Just a second.
Yeah, I sent you a link to it.
Yeah, thanks. So, right. All right. So I got a all right, just a second. Right. Right. So what about it? Where is it? Yeah, I
Wait,
got
yeah,
it.
my mic's. Oh, okay.
Yeah, yeah, got it.
Shit,
So,
my mic was okay. My mic is higher now,
all
or
right, all
it's
right.
better now. Okay.
Yeah, yeah, yeah. Now it's even better. Yeah,
The there is a logarithmic scale based upon how close my mouth is to my microphone. Like it's dramatic.
yeah.
Um, so it has to be really really close.
Yeah.
Otherwise, yeah. Okay, that's better. Okay.
All right. So, I would just have to go down and down a bit. So
So
like, can you point to the
it
like,
it
who?
it was a Guardian jackpot.
Oh, all right,
Um,
all right,
um,
got it. So the Big Bounce theory, all right, Big Bounce theory of cosmology, previously called the Big. All right. So like, is he asking about? Yeah. So he's asking about the Big Bounce theory. All right.
oh, okay. The big bounce theory.
Yeah.
Okay.
Yeah, yeah. So the big bounce is like a different kind of so actually let's take a step back, right?
Okay.
You discussed about the conformal cyclic cosmology theory, right? So like the big bounce is another example of a cyclic cosmology. So we have a few theories where the universe has an expanding phase, then it also has a phase of contraction. In the case of conformal cyclic cosmology, it doesn't contract as much. Uh, However, in the big bounce case, what happens is you have, rapid expansion like we currently have. But then there comes a time when a turnaround happens, and you have the universe starting to contract, but it does not collapse to a singularity like we have in the case of the Big Bang, right? So the Big Bang starts off with a so-called Big Bang singularity. That does not happen in the case of the Big Bounce. It almost comes to the point of a singularity collapse, and then the universe moves again. So it starts to so like it becomes very large, and then it starts to contract, and like it comes very close to like going back to some kind of a singularity, and then boom, the expansion starts again, and this cycle keeps on continuing. So like that is crudely how this works out. uh, it's actually very interesting because you can actually connect the big bounce theory with dark matter, and uh, it's it has quite a cute connection, because then you can measure dark matter using something known as big bounce genesis, which is an a very active area of research. I mean, uh, like it is as recent as like the 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 late 2010s. So yeah, we have quite a strong field of research on that topic as well. Uh,
So,
However, yeah,
um,
continue.
so Guardian Jackpot here has made the statement that there is no dark matter. I solved
All
the
right,
problem with Newton's formula in 2018,
all right.
which necessitates the solution provided by dark matter.
Yeah.
It's
All
it's
right.
it's a
That's great.
it's a
That's
misnomer
great.
to label it as dark matter problem instead of the T slash
Right,
DM solution.
right,
If
right.
I mean, you can say whatever you want. I don't know,
No,
but
I mean, yeah. So, yeah. So, I mean, I do not want to sound pessimistic in any sense. I mean,
okay,
it's good that people are thinking about this stuff. I mean,
okay.
at the end of the day, there is. I mean, I do not support any kind of I mean, there should be, like a level at which you need to know stuff before you start to say about this stuff. But I never like, let's say if I were to get some email from someone that I have attempted to solve dark energy or like inflation or stuff like that, I would definitely always try to at least listen to them and like what they have to say. Of course, I also review papers written by seasoned theoretical basis. I mean, when you try to get published in physics, you go through something known as peer review, where physicists who are equally or even more accomplished than review your work.
Mm-hmm.
So I review different papers from different people, and different people review my work. And like, if my work is good enough, if my work is fine, then it goes through that and it gets published, and if it is not, I have it could get rejected, and I have to improve. So that's how science works in general. However, Newton's formula being used to explain dark matter is actually not a bad way to go about it, and a lot of seasoned physicists also subscribe to that approach. It is known as modified Newtonian dynamics, or MOND. So this approach was like initially started off in the 70s and 80s by Milgram, and Mond has now gathered quite a big literature. Of course, there are people who do not support Mond, right? But there are people who also do support Mond, and people work on Mond theories very sincerely, and some of my own collaborators work on it. So modifying Newton's formula, or like using it to like explain dark matter, is not the worst way to go about it. And I would actually recommend the person who commented it to read papers about Mond, and like he or she might find it very interesting.
How do you spell that?
Mond, so it is
Oh, Mond.
modified Newtonian dynamics, MOND.
Okay.
Right.
Interesting. Okay. Um, do let's see. So there's some questions. Okay. I have a question.
Yeah.
I'd like to ask a crazy question.
Sure, sure, sure.
You know, I forgot what this theory was called. So, if you look at what life is, we're gonna go to this route. If you look at what
Yep.
life is, life seems like it has this quality of not, I wouldn't say resisting entropy, but surfing entropy, because we ingest stuff, it comes out. However, at the same time, life also has this quality where it seems like it's like, if you look at our planet, it appears to be expanding as much as it can into every crevice that there is, for it to just keep continuing. Um, in a way, it almost seems like life has properties, or entropic properties, within, like, inherently. Um, One of the theories, and I saw this on like a Wikipedia article, was that at the end of the universe, everything would become quote unquote uh, conscious, which I define consciousness as the integration of differentiated information. Um, but you could maybe say the word life or something. I don't know, something like that. But if taken to the extreme, um, like, does this make any sense at all? Or um, it's odd to me that life seems to have similar properties as to spread as entropy does, or to expand. Um, I could also be
Right.
missing something there. I'm not sure.
I mean, I, I mean, if you think about it, entropy, is really how, like defining it in the very simplest way possible. It is like, how disorder, you know, uh, gets spread out.
Okay.
But if you want to talk about it from the like from a more physical point of view, it's like how information gets spread out.
Yeah.
And so, all of us, whether it's you or me, we are all made of particles, and particles, constitute information in a sense. So it is a natural thing that life spreads out in a similar way, because you know uh even simple galaxies, even objects, like molecules and all that, all of them try to increase their entropy, which is like innately related with the second law of thermodynamics. And so, seeing that life behaves in a similar way, from that entropic point of view, is not that much of a surprise, because at the end of the day, we are also the same things governed by the same thermodynamics, and so is life. At least that's my view.
In terms of information,
Yeah, 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 indeed.
although, like, we don't. Hmm. Although I think a certain quality of life is that it's very good at retaining the information as it spreads out,
Yeah,
um, and correcting things. That is an interesting thought, though.
yeah, indeed.
I hadn't thought about that before. Um, okay. Oh shit. Okay. 1 second. Zoom meeting died. Just I got this one. This is why there are ads, guys. The volume on my microphone or the volume on whose microphone? because I am seeing myself peak in OBS. I can't manage add like when to add ads as I'm talking and stuff. It's just set to what YouTube does. Otherwise I'd be juggling like 5 things. There is always YouTube Premium. Yes, the food kills itself. It wants to be your food. Yep. Time under Google the Hitchhiker's Guide to the Galaxy. You'll find a link to the. Okay. Okay. Oem is back in the meeting. Oh, Newton's formula still holds water. It's still showing that? Oh. You're back.
Yeah.
Okay. Yeah, you know what? I'm gonna hit up Brilliant. No, they're telling me to hit up a sponsor.
Sure.
So, okay. What? Okay, let's this guy is talking about the Hitchhiker's Guide to the Galaxy. Okay, so we're back to Guardian Jackpot. He feels very strongly about this. The modification to Newton's formula is classical and doesn't get into quantum. People are going to be surprised and say, why didn't I think of that? Or why hasn't anyone? It's so simple, it's silly.
Okay.
Would you
So like
go back?
should I? All right. So like should I
Would you go?
address that?
Well, would you go back to saying like maybe sometimes it's a good idea to understand more of the territory of something before assuming that what you see is the only reality?
Yeah, I mean, so all right. So I would say it's a twofold thing, right?
Okay.
Uh,
He does have
so
he does have a follow up, by the way. Let me just say this:
yeah,
the
all right.
the corrected formula is only useful if leaving the relatively local area of Earth where Newton's formula presently still holds water. It's only monetizable to someone leaving Earth, like SpaceX to Mars.
So I mean that is actually what MOND does.
Oh, okay.
So yeah, indeed, it is more or less exactly that because in modified Newtonian dynamics, they propose that the ideas of Newton become relevant at the scales at which we are seeing dark matter. And so, the curves by which, we are interpreting that there is additional matter in the galaxy, those curves can be explained if you have, like let's say just a different form of the gravitational force. And yeah, that is a simple idea. However, now MOND can explain dark matter, right? But then it runs into problems when it wants to explain the other things. Because if you are, proposing a theory to explain dark matter, then why only dark matter? It should be a theory for the universe, right? And so if your theory is like proposing to explain dark matter, it should also explain dark energy. It should, also work with the other things. But MOND cannot, in most cases, work in a amicable way with dark energy and the other theories. And so, that's where it runs into issues. And so that's why, I would like to, suggest Guardian Hunter, to like, actually, have some read about Mond, because I think they will genuinely, be fascinated by the theory and possibly would like to, read more about it, and maybe someday, contribute to its understanding as well.
Okay, okay. I think I'm at this point it's a little late for me. I know it's extremely late for you. Um, I think this was really cool. I think we'll do this again. And we'll have a, we'll probably think of more stuff to talk about. Um, and as as I publish more videos, the channel will kind of get back to where it was. It just takes a little bit of time and some effort.
Yeah. Yeah.
Um, yeah, it'd be cool to have tons of viewers. Um,
Yeah, sure.
but yeah, okay. It was a pleasure talking to you, Om. Thanks a lot for your time, and thanks a lot for sleep depriving yourself. Um, um, I'm gonna go
No,
ahead and yeah.
and thanks a lot to you again for like inviting me for this, and for all the people who actually joined in, because so we are basically, two kind of insane people just rambling about some random shit about the universe, and still, like our shitty talk became at least some kind of an interesting escapade for them. So yeah, thanks to everyone.
Yes. All right, I'm gonna end the stream. And
All right.
and drink some water.
Yeah.
All right.
Jake's the rest.
Yeah. All right. See you later, man. Thanks a lot.
Yeah, man. Bye.